everybody. My name is Emeka Wabigu, and I'm here to talk about microkinetic modeling as a tool for catalyst discovery. Okay, just take out this.
Just put chop.
And just Emeka. That's what I go by, Emeka.
Emeka, okay.
Alright, there's a background story to my name, but that's for another day. Alright, we good? Okay, a brief outline of what I'm going to be talking about today. I'm going to give you the purpose and the background of modeling, and then we're going to talk about the method that they use to discover the catalyst for a certain reaction, and then I'm going to give you the results of the experiment, and then I'm going to tell you why it's important, the discussion and conclusion, and tell you why it's important, and what you need to know. So, does anybody know anything about microkinetic modeling or modeling in general? Anybody does work on modeling? Okay, the reason why y'all don't know much about it is because it's dry chemistry. Meaning, we don't do any reactions. We don't go work in the lab, we don't stand for 3 hours. Everything is done on computers. So, definition of microkinetic modeling. This is the simplest definition, and actually it doesn't really serve it justice. But it's pretty much a procedure to model a reaction system. Now, supposing you want to know what happens when everybody knows this, but supposing you want to know what happens when you react hydrogen with oxygen and you get water, wow. But what if you don't know the outcome of a reaction? What do you do? What if you don't know the type of products that happen that come out? What do you do? That's where modeling comes in. They do simulations, and how they do the simulations are they base their work on theories, chemistry theories, and physical theories that describe reactions and interactions between atoms and molecules. So that's exactly what I just said. It's based off of the density functional theory. Is a theory that describes, like I just said, the interactions between molecules, if you're dealing with clusters, a system, or just atoms if you're dealing with just elements. And then parallel kinetics as well is to tell you how fast, that's also something modeling tells you how fast a reaction can occur. So that's where parakinetics comes in. So, like I just said, it's used to describe surface chemical reactions. And when you talk about surface chemical reactions, they're talking about how the reaction they're talking about the mechanism of the reaction, pretty much. And then they use the modeling to tell us about the activity or the selectivity of the catalysts in the reaction. And then they compare one catalyst to another based on the results. Okay, everybody good? Everybody have an understanding of microkinetic modeling? Okay. So, everybody should know this one. What is a catalyst? Okay, I'm guessing it's because it's 8 a.m. in the morning, that's why. All right, pretty much a catalyst is any substance that accelerates a chemical reaction without being affected, right? So how does a catalyst do all this work? How does it work? How do catalysts work?
It lowers activation energy.
Exactly, it lowers activation energy. But what must happen? What must happen first of all before a catalyst can lower activation energy of a reaction? Well, the first thing that must happen is in every chemical reaction, before you can get the products, the reactants, the bonds have to break. They have to dissociate. So the reaction I'm going to be talking about soon is the decomposition of ammonia. So first of all, you have to break up the NH bonds to go back to nitrogen and hydrogen. And then the breaking of the bonds, they require energy, and that's where Frank came in just now and said that they lower activation energy. All right, but still, this doesn't tell us how the catalysts work. So, how catalysts work by providing an alternate reaction path, or pathway, between the products and the reactants and products. So generally, they just generate a different way for the reaction to take place. Okay, and this is done by forming an intermediate. So So now the method. So in the paper that I reviewed, they determine, I'm sorry. Catalysts are determined by the electronic structure. So they take different elements and then they look at the characteristics based on the theories that I was talking about. And then it turns out that ruthenium was a very good catalyst for the decomposition of ammonia. And the other element that they tried against, they compared it to iron, which they're in the same group, so I'm guessing it's because ruthenium was bigger. And I know they already talked about, the other presenters today talked about doping of, alloys with ruthenium, so I'm guessing ruthenium has definitely has some sort of special characteristics. But some of the things you should know about it, because the reaction occurs at the surface, you need to know the crystal lattice structure. That's what we've been talking about, unit cells. It's a simple cubic, and then this is where it is in the periodic table, and all the elements, electrons. So again, everything, like I said, it's dry chemistry, so everything was done on computers. So they ran simulations of what happens when they put ruthenium with ammonia. And this was the alternate reaction mechanism that occurred. They had 11 steps. No, sorry, 12 steps. 12 mechanisms. 12 steps in the mechanism. And then how the modeling now works is they take that's where the kinetics comes in. So now you know about the density function theory. So this is where the kinetics comes in. They go and find the limiting step, or the rate determining step, sorry, that's the word. Rate determining step. And then they do some calculations based on the theory. So, like I just said, it was simulated and they used it to describe the trends for ammonia synthesis and decomposition kinetics. So this is a graph that showed the results. So these are other models that people had done in the past. And these other models are based off of different, maybe another theory, probably not as accurate theory. Could be maybe they solved the Schrodinger equation or did approximations. And then this was, these dots here, these are the experimental values that they got. This is when they actually did the experiment, not ran the simulation. And then where is the model? This is the model that they did. So as you can see, it was closest to the experimental results. Okay? So like I just said, the model that they developed was close to the experimental value. And it also served a way to compare the results from the density functional theory. So other methods, the other models, were not as accurate. And like I said, it's possibly due to the fact that they used different theories or something was just wrong with the program. So now, we know that ruthenium now is a better catalyst for the ammonia decomposition, and it was validated with experimental procedures. But there is a problem with microkinetic modeling. The problem is it only simulates what will happen in a reaction, which is good, but it doesn't tell you exactly like the purity. It doesn't tell you like the purity of the compounds. It doesn't tell you, quality. It doesn't talk about the cost of production. It doesn't talk about the byproducts, and it tells you, okay, this is what happens when you react, catalyst in a reaction. So these are just some of the problems that they encountered. And if I was to write a proposal, I would say that they should focus more on finding a way to, find a better quality, to produce better quality, and put some cost equations in there, based off of the reaction, I guess. And that's it. Oh, wow, questions.
Rico.